My dear students, welcome back to our channel. In this video, I will be explaining the Bachelor of Computer Applications 4th semester subject Artificial Intelligence as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 3, first important short question is: define monotonic reasoning. Monotonic reasoning is a type of logical thinking where, once we add new information to a system, we never take away any conclusions. In other words, the more facts you add, the more conclusions you can make, but you can never undo any conclusions that have already been made. Example: imagine you are solving a puzzle. You start with the fact John is at the park. Then, you add John likes ice cream. As you add more facts, you can keep making conclusions, like John may want to eat ice cream at the park. Even if you later learn new information, like John is on a diet, it doesn't change the old conclusions. In monotonic reasoning, new information only adds to what you already know, and your conclusions can't go backward. Easy tip to remember. Monotonic reasoning is equal to more info is equal to more conclusions, but no going back. It's like building up your knowledge without ever removing anything. Next important short question is: 2. What is non-monotonic reasoning? Non-monotonic reasoning is the opposite of monotonic reasoning. In this type of reasoning, new information can change or undo previous conclusions. This is important because the world is not always predictable, and new facts can sometimes contradict what we thought was true earlier. Example: imagine you believe all birds can fly. Old conclusion: a penguin is a bird, so it can fly. Later, you learn that penguins can't fly. Now, your reasoning changes, and you conclude penguins are birds, but they cannot fly. In non-monotonic reasoning, the new information, penguins can't fly, causes a change in your previous conclusion. Why it's useful? This type of reasoning is useful in AI systems because the real world is full of exceptions and facts change over time. It allows AI to adapt and revise conclusions when new facts come in. Easy tip to remember. Non-monotonic reasoning is equal to new info changes old conclusions. It's like adjusting your thinking when you learn something new. Next, Unit 3. Long questions. First important long question is: 1. What are the logics for non-monotonic reasoning? Non-monotonic reasoning allows us to make conclusions that can change when new information is introduced. Unlike monotonic reasoning, where new facts only add to previous conclusions, non-monotonic reasoning helps AI systems adapt to new situations or revise their thinking when facts change or exceptions appear. There are several logics used to handle non-monotonic reasoning, and each has its own way of managing how conclusions are revised. 1. Default logic. Default logic is used when we make general assumptions, but these assumptions can be overridden if we receive new information. It's like saying, most birds can fly, but if we learn that a specific bird, like a penguin, cannot fly, we can change our conclusion. Example: default assumption, all birds can fly. New fact, penguins cannot fly. Revised conclusion, penguins are birds but cannot fly. 2. Circumscription. Circumscription is a method used to minimize the number of exceptions in a given set of rules. It's like saying, assume everything behaves normally, except when proven otherwise. This approach helps AI make conclusions based on typical cases, while still being flexible enough to handle exceptions. Example: normal assumption, if a creature is a bird, it can fly. Exception: penguins are birds, but they don't fly. 3. Autoepistemic logic. This logic is about self-reflection. When an AI system reasons about what it knows or doesn't know, it can conclude, I don't know if this is true or false, and update its reasoning as it learns more. Example: AI knows penguins are birds. AI doesn't know if penguins can fly, so it says, I am unsure about whether penguins can fly. Later, AI learns new facts and adjusts its conclusion. 4. Non-monotonic modal logic. This type of logic involves possibilities and necessities. It helps AI reason about what could be true or what must be true, considering different possibilities. It allows reasoning about changes or uncertain information. Example: possible conclusion, penguins may not be able to fly. Necessity conclusion, in the current world, penguins cannot fly. Why these logics matter? These logics make AI more flexible in dealing with real-world situations where things are not always clear-cut or fixed. AI needs to be able to adapt when new, sometimes contradictory, information arises. These logics help AI revise its conclusions to reflect new facts, making it more intelligent and realistic. Easy tip to remember: non-monotonic logic is equal to changing conclusions when new facts appear. It's like changing your mind when you learn something new. Next important long question is: to discuss about depth-first search with suitable example. Depth-first search, DFS, is a search algorithm used in artificial intelligence, AI, to explore a problem space, like a maze or a network of cities. DFS explores as far down a branch of the search tree as possible before backtracking. It's like diving deep into one path, and if that doesn't work out, you go back and try another one. How DFS works: 1. Start at the initial state, root of the search tree. 2. Go deeper into one branch, explore all possible moves in that direction. 3. If you reach a dead end or a solution, either backtrack or stop. 4. If needed, return to previous steps to try other paths until you find the solution. DFS uses a stack, a data structure, to remember where to go next. It adds the next nodes to the stack and pops them out one by one as it goes deeper. Example: imagine you are in a maze and need to find a way out. The maze is represented like this: start ABD, CEF exit. Start at the start point. Go to A, then B, then D. Dead end at D, so backtrack to B. Move to C and then try going deeper into E. Finally, reach the exit. The DFS explores each path deeply, backtracking when it hits a dead end until it finds the solution. Advantages of DFS: 1. Memory efficient. DFS doesn't need to store all nodes at once, like BFS does. 2. Simple. It's easy to implement using a stack. Disadvantages of DFS: 1. May not find the shortest path. DFS may get stuck in deep paths and take longer to find the solution. 2. Risk of infinite loops. If the tree has cycles, DFS may go in circles without reaching the goal. Real-life analogy: imagine you are exploring a new city, and you decide to visit each street one by one, walking as deep as possible down each street before returning to check another street. This method is DFS. Tip to remember: DFS is equal to go deep, backtrack if stuck. DFS is great for problems where you want to explore deeply into possible solutions, but it can be inefficient for finding the quickest route. Next important long question is 3. Explain about BFS algorithm. Breadth First Search, BFS, is another popular search algorithm used in artificial intelligence, AI. Unlike Depth First Search, DFS, which goes deep into one branch before backtracking, BFS explores all the possible paths level by level. This means it first checks all the neighbors of the starting point, then the neighbors of those neighbors, and so on. How BFS works. 1. Start at the root node, or starting point. 2. Explore all immediate neighbors of the current node first. 3. Move to the next level and explore all the neighbors of the neighbors. 4. Continue exploring level by level until the goal or solution is found. BFS uses a queue, a data structure, to remember the nodes to explore. A queue works like a line where the first element added is the first one to be processed, FIFO, first in, first out. Example. Imagine you are trying to find the shortest path in a maze. The maze looks like this. Start at start. Level 1. Explore all immediate neighbors A. Level 2. Next, explore neighbors of A, B and E. Level 3. Explore neighbors of B and E, C, F. Level 4. Explore neighbors of C and F, D, G. Finally, reach the exit. BFS ensures that you explore the shortest path first because it looks at all the possible paths step by step. Advantages of BFS. 1. Finds the shortest path. BFS guarantees the shortest path in unweighted graphs because it explores level by level. 2. Simple and systematic. It explores each possible option and doesn't miss anything. Disadvantages of BFS. 1. Memory consumption. BFS stores all nodes at each level in a queue, so it can use a lot of memory, especially for large trees. 2. Slower for deeper nodes. If the solution is far from the root, BFS can take time because it explores all nodes at each level. Real-life analogy. Imagine you are looking for a friend in a crowded room. Instead of searching each person one by one, you first look at everyone in the front row, then the next row, and so on. This way, you are sure to find your friend in the least number of steps. Tip to remember. BFS is equal to explore level by level, find the shortest path. BFS is great for problems where you want to find the shortest route or solution, but it may take up a lot of memory for large problems. Next important long question is 4. Explain about probability and Bayes theorem. Probability is a concept used to describe how likely an event is to occur. It's a measure of uncertainty. For example, when you flip a coin, there is a 50% chance, probability, that it will land heads up, and a 50% chance it will land tails up. In artificial intelligence, AI, probability helps machines make decisions based on uncertain or incomplete information. AI systems use probability to predict the likelihood of different outcomes and choose the most likely one. Bayes theorem, what is it? Bayes theorem is a powerful tool in probability that helps update our beliefs based on new evidence. It shows us how to calculate the probability of an event given prior knowledge and new data. Bayes theorem is written as PAB is equal to PBA times PAPB, where PAB is the posterior probability, the probability of event A happening given that B has occurred. PBA is the likelihood, the probability of event B happening given that A happens. PA is the prior probability, the initial probability of a happening before seeing the evidence. P, is the evidence or total probability of B happening. Example. Let's say you want to know the probability of someone having the flu, A, given that they are coughing, B. P, the probability that someone has the flu, say 10%. P, B vertical bar are the probability of coughing if someone has the flu, say 80%. P, B the probability of someone coughing in general, say 20%. Using Bayes' theorem, we can calculate the probability of having the flu if the person is coughing. PAB is equal to PBA times PAPB is equal to 0.8 times 0.10.2 is equal to 0.4. So, there is a 40% chance that the person has the flu if they are coughing. Why is Bayes' theorem important in AI? In AI, Bayes' theorem helps systems make informed decisions based on data. For example, spam filters in emails use Bayes' theorem to decide if an email is spam by considering past data, such as words in the email, and updating their beliefs based on new emails. Easy tip to remember. Probability is equal to likelihood of events. Bayes' theorem is equal to updating knowledge with new evidence. Probability and Bayes' theorem make AI smarter by allowing it to learn from past experience and adjust its beliefs with new information. Next important long question is 5. What is a Bayesian network, and how does it relate to AI? A Bayesian network is a powerful tool in artificial intelligence, AI, used for probabilistic reasoning. It helps AI systems make decisions or predictions based on uncertain or incomplete information. It is a graphical model that shows how different variables, or factors, are related to each other using probabilities. What is a Bayesian network? A Bayesian network, BN, is made up of two main parts. 1. Nodes. These represent variables or factors, like a disease, weather, or sensor reading. 2. Edges, arrows. These show the relationships between the nodes. The arrows indicate how one node, or variable, influences another. Each node has a probability associated with it, which represents the chance of a particular outcome or event. Bayesian networks help AI systems understand how different pieces of information affect each other and how new information can change predictions. How does it work? Bayesian networks use conditional probability. This means that the probability of one event depends on the occurrence of other events. For example, if we know a person has a cough, the probability of them having the flu might increase. Example, medical diagnosis. Imagine a Bayesian network for diagnosing a disease. Nodes. Cold, see whether the person has a cold, true, false. Cough, whether the person has a cough, true, false. Flu, F, whether the person has the flu, true, false. Relationships, edges. A cold might increase the chance of having a cough. Having a cough might increase the probability of having the flu. The network will look at the relationships and calculate the probability that a person has the flu based on symptoms like cough and cold. For instance, P, flu vertical bar cough is equal to true, cold is equal to true, could give the probability that a person has the flu, considering that they have both a cough and a cold. Why is it important in AI? In AI, Bayesian networks are useful because they allow the system to handle uncertainty. Instead of making a decision with 100% certainty, AI can work with probabilities and update its beliefs based on new data. This is particularly important in areas like medical diagnosis, predicting diseases based on symptoms, weather forecasting, predicting weather conditions with uncertain data. Robotics, making decisions in uncertain environments. Easy tip to remember. Bayesian network is equal to a way to make decisions with uncertainty using probabilities and relationships. Bayesian networks help AI systems think more like humans, who often make decisions based on uncertain or incomplete information. Next important long question is 6. Give the certainty factors and explain the rule-based systems. In artificial intelligence, AI, certainty factors and rule-based systems are important concepts for decision-making and reasoning. Let's understand them in simple terms. Certainty factors. Certainty factors, CF, are used in AI to measure the degree of certainty or confidence in a conclusion or decision. In the real world, we often have incomplete or uncertain information, and certainty factors help us deal with this uncertainty. A certainty factor is a number between 0 and 1. 0 means there is no certainty about the conclusion. 1 means the conclusion is certain or guaranteed. Any value between 0 and 1 represents partial certainty. For example, let's say a doctor's diagnosis system is trying to determine if a patient has the flu. Based on symptoms, fever and cough, the system might assign a certainty factor of 0.8 to the conclusion that the patient has the flu. If the system later finds that the patient has been in contact with others who are sick, it might increase the certainty, example, to 0.9. If the system finds no other flu-like symptoms, it might decrease the certainty, example, to 0.6. Certainty factors allow AI systems to make decisions even when the information isn't 100% certain. Rule-based systems. A rule-based system is a system that uses if-then rules to make decisions. It's like a collection of rules that guide the AI system to draw conclusions or take actions based on the given data. The basic structure is: if some condition is true, then perform an action or draw a conclusion. For example, in a medical diagnosis system, the rules could be: 1. If the patient has a fever and a cough, then they might have the flu. 2. If the patient has a sore throat and a cough, then they might have a cold. These rules are combined with certainty factors. When the system applies a rule, it can adjust the certainty factor to show how likely the conclusion is based on the conditions. Example: let's say we have the following rules in a medical expert system. Rule 1: if the patient has a fever and cough, condition, then they have the flu, conclusion, with a certainty factor of 0.8. Rule 2: if the patient has a sore throat and cough, then they have a cold with a certainty factor of 0.6. Now, if the patient has a fever and cough, Rule 1 will fire, and the system will conclude with a certainty factor of 0.8 that the patient has the flu. Advantages of rule-based systems. 1. Simplicity. They are easy to understand and implement with clear, logical rules. 2. Transparency. The reasoning process is visible and explainable. Disadvantages. 1. Limited flexibility. Rule-based systems work well for structured problems but are less effective when dealing with complex or unstructured data. 2. Scalability. Managing a large number of rules can be difficult. Easy tip to remember. Certainty factors is equal to degree of confidence. Rule-based systems is equal to if-then rules to make decisions. These concepts help AI make decisions even when there is uncertainty, making them useful in applications like medical diagnosis, expert systems, and more.